Hello, welcome all. Welcome to the online lectures of nanoelectronics. So this is the second part of module 5. In the previous video session, we have discussed about the parallel transport in nanostructures. So in this module, in this session, we will discuss about the perpendicular transport in nanostructures. So earlier, we have discussed that during the parallel transport, if the moment of charge carriers is, if it is parallel to the interfacial plane, it is called parallel transport. If the moment of charge carriers is perpendicular to the interfacial plane, it is called the perpendicular transport. So consider a quantum well. The electrons will be trapped inside the quantum well. So if the moment inside the quantum well, that will be parallel, but some of the trapped electrons in the quantum well can cross the barrier. That means some of the electrons can move through the barrier. Even with the insufficient energy, some of the electrons can cross the barrier. That is called the tunneling effect. So carriers in the 2D gas of electrons in the interface of a heterostructure can move in a direction perpendicular to the plane. That is a tunneling. That means some electrons trapped in the quantum well can jump over the barrier that is perpendicular to the interfacial plane. So quantum mechanically, a particle with insufficient energy can also cross the barrier. Not all the electrons, very few electrons, some of the electrons can tunnel through the barrier. If the barrier thickness is very thin, more and more electrons can cross the barrier. That is, tunneling increases. In tunneling, a few carriers cross the barrier with energy less than the barrier height. Please note it. Even though there is some barrier, some of the electrons trapped in the quantum well can also cross the barrier, jump over the barrier that is perpendicular in direction. So quantum tunneling is a perfect example for perpendicular transport. So consider a quantum well. So focus here. Gallium arsenide is sandwiched between two wideband semiconductors, L-gas here, left and right side. So there is a barrier here also a barrier. So here quantum well is formed here. And the extreme left also there is gallium arsenide narrowband. Extreme right there is again gallium arsenide. So by default there is a barrier here. So some of the electrons can in the gallium arsenide here can cross the barrier and can move towards the quantum well. Same manner, with the same manner, from extreme right, gallium arsenide will have some electrons. That electrons can also move this barrier. So there will be tunneling. Consider a quantum well formed by gallium arsenide layer sandwiched by L-gas. Here the E1 is represented as the ground state, minimum energy level of the quantum well. So here the EF represents the Fermi level. One thing you need to note is that the EF, the Fermi level, and the ground state energy level of quantum well is not aligned here. Even though it is not aligned, some of the electrons still can move through the barrier. So there will be definitely there will be tunneling. If the Fermi level and the ground state energy level, if it was aligned, then the moment will be maximum. The tunneling will be maximum. Moment of electron is the current. The tunneling current will be maximum if it was aligned. EF and AN was aligned. So how you can align these energy levels? Yes, you need to externally apply some electric field. Anyway, this tunneling is called the resonant tunneling effect. Now we can look into the IV characteristics of resonant tunneling effect. So consider you are applying some external electric field between these two leads, left and right leads. Here I have plotted one IV graph, voltage versus current graph. When you apply external electric field, what will happen? There will be energy bending. Also there will be tunneling effect. That means the electrons from here will move through the barrier. So the movement of electrons, that is called the current. Even without electric field, there will be tunneling. When you apply external electric field, actually you are supplying more and more electrons to gallium arsenide. So the movement of electrons increases, tunneling increases based on the applied electric field, based on the applied voltage. If you increase voltage, more and more electrons will cross. That means tunneling current increases. At the same time, the Fermi level will be shifted. That is represented here. There will be bending. Fermi level position is moving upward. That means EF and E1 is trying to get aligned. So when you increase voltage, the tunneling increases. That means the current increases. At a particular point, look here, this point, focus here. EF and E1 is aligned. That means the tunneling will be maximum. This energy bands are now, it is get aligned. The movement of electrons is maximum. The tunneling will be maximum. At this point, the particular voltage will be, applied voltage will be 2 E1 divided by small e. E1 is nothing but the ground state energy level of quantum well. So important point is that when the energy bands EF and E1 is get aligned, the current will be maximum. The resonant tunneling current will be maximum. That particular voltage is 2 E1 by E. What will happen if we further increase the external field, the external voltage? EF is moving further upwards. That means now the EF and E1 is not aligned because EF is moving upward. So the reverse effect, what will happen? If it is not aligned, gradually the current is decreasing. Again decreasing. After the breakdown, what will happen? There is no control over the current, suddenly increases. So there is a valley, then a peak. So I will explain again. When you start applying voltage, the tunneling increases. When EF and E1 is get aligned, the current will be maximum. At this point, look here, at this particular voltage, the current will be maximum, the peak. That is EF and E1 is get aligned. If further increasing bending increases, EF moving upwards based on the applied electric field E into V. So the reverse effect. Now it is not aligned. EF and EN is not aligned. So the tunneling decreases. If you further increases, shifting increases, tunneling current decreases. After the breakdown, there is no control over the current, suddenly increases. So this resonant tunneling effect is used in the fabrication of RTDs, resonant tunneling diodes, that will be discussed in module 6. During this tunneling effect, electrons will move periodically. There will be oscillations. That oscillation is called the Bloch's oscillation, and that is also an important point. The exam point of view, you need to note this point, Bloch's oscillation. The Bloch's oscillation is the phenomenon of periodic motion of an electron in narrow miniband of superlattice induced by an applied electric field. What is superlattice? So a combination of multiple quantum wells, that is called the superlattice. So if you're repeating this structure again and again, stacked layers of multiple quantum wells, that is called the superlattice. So the movement of electrons, periodic movement of electrons, there will be oscillation. That oscillation is called the Bloch's oscillation. Now we will move to the next topic, that is we will focus on the quantum transport. Quantum transport occurs when nanostructures are connected to an external field, external current, by means of leads. In order to observe quantum transport, the effective mass of electron should be very small to guarantee high mobility. That means in gallium arsenide also, if we take gallium arsenide, when compared with gas, aluminum gallium arsenide, the mobility of electrons is very high. One point is that the effective mass of electron in gas is very small when compared with gas. When the effective mass decreases, the mobility also increases. That is advantage of gallium arsenide over gas. Energy levels in quantum well increases with decrease in effective mass. That's also a valid point. Then if the dimensions of the nanostructures are very small, that means take a nano wire. If the length of the wire is less than the mean free path, then the collision will be minimum. So scattering will be very less. Theoretically there will not be any scattering. So what do you mean by mean free path? Mean free path is nothing but the average distance between two successive collisions of electrons. The average distance between two collisions, that is called the mean free path. If the length of the wire is less than this mean free path, theoretically we can say that there is no collision inside the quantum wire. Theoretically there will not be any collisions. That's also an important point. So here consider two reservoirs, extreme left and extreme right. There is a collection of electrons. This is called represented as a reservoir, a semiconductor shield. Reservoir 1 here, reservoir 2 here. These are connected by a bridge, conducting path. That bridge is nothing but a quantum wire. So we know that the quantum wire is one dimensional. One dimension means we have restricted two sides. Two sides means two axes. We shrink to a nanometer size. So that is called the one dimension when compared with the 3D. The 3D means normal semiconductor devices. If you diminish one axis to nanometer, under 100 nanometer, it is called 2D, quantum wire. If you diminish two axes to nanometer, especially less than 100 nanometer, it is called one dimension. So this quantum wire is a 1D device, 1D structure, 1D nano layer. So it is called this quantum wire is called one dimension. So if the length of this quantum wire is less than mean free path, theoretically there will not be any scattering. The region without scattering is called the ballistic region. That's also important thing. If the quantum wire's length is less than mean free path, there is no scattering, and such transport is called ballistic transport. That region is called the ballistic region, and the transport without collision is called the ballistic transport. So here another important question will be explain and derive the Landauer formula. Very important exam point of view. The previous university question was explain and derive the Landauer formula. So first of all you need to draw this figure, then you need to explain it. So the conduction of electrons through the quantum wire can be expressed through the Landauer formula. We will look into that. So the current through the quantum wire can be expressed as the product of concentration of electrons. So the concentration of electrons in a quantum structure will get from the density of states. obtained from the density of states function, that is represented N1D. Focus here, N1D with respect to energy, that is in bracket E, in the energy interval EV, N1D EV into the moment of electron, that is the velocity of electron, and the unit electronic charge, that is Q. So here it is expressed, the current moment of electrons, that is current, equal to N1D, that is density of states dose of the quantum wire is in one dimension, that is expressed as N1D in electron volt EV into the velocity, this small v, that is velocity, please note it, velocity of electron into this gives a charge. The charge of electron, we know that it is E into density of states into a velocity in electron volt, that is equation number 1. Then the density of states of one-dimensional structure, that is already derived in module 1. So I will directly express the equation here, that is N1D is equal to 1 by pi h cut into root of square root of 2me by capital E, that is energy. Then me, we know that, what is that me? That is effective mass of electron, effective mass of electron. Then energy is equal to, we know that half mv square, that is 1 by 2 into mass of electron, small v is nothing but the velocity. From this equation, E is equal to half mev square, we can express the velocity as v is equal to square root of 2e by me, that is equation number 3. Now we can substitute the value of N1D, that is from equation 2, and velocity from equation 3. We can substitute these values to the equation number 1. One thing you need to note while substituting these values, be very careful. When you derived this equation N1D in the module 1, we considered that electron was spinning, electrons had 2 states. So during that derivation, we substituted a factor 2 in order to represent the electron spinning. Electron had 2 states. We know that electron is oscillating, it is fluctuating, electron is spinning. But here in this quantum wire, we assume that electron is moving through a straight path. Instead of spinning, we assume that, simplicity, Landauer assumed that the electron is moving in a straight path. So you need to cancel out that factor 2 here while substituting. You have to be very careful about that. I will explain it here. When you substitute here the N1D, that is 1 by pi h cut square root of 2me by e into 1 by 2, that means you are cancelling out the 2 factor which have substituted earlier during the in the module 1. So be careful about that. Then the velocity into ev, v here, then e is already there, that is the previous slide, e into e square, so e square, the remaining thing. From that we can write I is equal to e square into v divided by pi h cut. Then also we know that, what do you mean by h cut? Small h, Planck's constant. So h cut is equal to simply h by 2 pi. So instead of h cut, we can substitute the value h by 2 pi. So finally we will get I by v is equal to 2 e square by h. What is I by v? That is conductance G. We will represent it as G. So the conductance in a quantum wire is 2e square by h. It's very important. The conductance 2e square by h. So the quantity 2e square by h is called the fundamental conductance. So Rolf Landauer shown that the electrical conductance of a quantum wire where electrons travel ballistically without collision is given by G is equal to 2e square by h. We can also substitute the values for the charge of electrons here, 1.6 into 10 raised to minus 19 and Planck's constant. So you will get around 7.746 into 10 raised to minus 5 Siemens. So 1 by conductance is equal to resistance. Quantum resistance also R is equal to 12.9 kilo ohm. So suppose if there are n channels, in the previous cases we discussed there is only one quantum wire. Suppose there is n channels, then the total conductance will be the basic conductance 2e square by h into probability of electrons crossing through the barrier. That is TNM, that is a transmission probability. So if there is n channels, you need to take the summation up to n channels. So TNM is nothing but the probability, mechanical transmission probability. So this is the final Landauer equation. You need to write this equation and derive the things from the earlier notations. So we have completed the Landauer formula. And what do you mean by the Landauer formula? So Rolf Landauer proposed and derived a basic conductance quantity in a quantum wire, that is 2e square by h. So in a quantum wire, the total conductance, if there is n channels, you need to multiply it with the 2e square by h into the probability. Then mechanical transmission probability is represented as TNM square. So this is the Rolf Landauer's formula, simply known as Landauer formula. Very, very important. So we have finished the perpendicular transfer, that is a part 2 of module 5. In the next session, we will explain about the Coulomb blockade and Aharonov-Bohm effect, the transmission of electrons while applying magnetic field. So these things will be explained in the next sessions. Thank you.